For almost a century, Tyrannosaurus was uncontested as the apex of carnivory. Other giant predators were known, such as Acrocanthosaurus, the enigmatic lost Spinosaurus and Carcharodontosaurus, and the mysterious reported Jurassic Giant, now possibly known as Allosaurus anax. But none were fully capable of standing in the same weight class as Tyrannosaurus. That was until a chance discovery in the land of giants offered up what might be the most gigantic carnosaur ever known. Still, almost 30 years later, the question lingers. Just how gigantic was Giganotosaurus, the giant southern lizard?
Giganotosaurus. Biggest carnivore the world has ever seen.
When Giganotosaurus was first revealed to the public in the early 90s, the timing couldn't have been better. The biggest blockbuster film of all time up to that point, Jurassic Park, had put dinosaurs back into the pop culture zeitgeist in a way they hadn't enjoyed in decades, and Tyrannosaurus was right up there in the limelight. This was also around the same time the current record for the largest known Tyrannosaurus was set by then new record-breaking specimen FMNH PR 2081, or SU. It surpassed prior famous specimens like the template for Jurassic Park's Star at the American Museum of Natural History, and the famous holotype specimen at the Carnegie Museum. For what seemed like the first time ever, there was another carnivorous dinosaur that might have been potentially even larger. Immediately, the two were practically pitted against each other like some ultimate heavyweight boxing match. Well, more like a slap fight considering their diminutive arms. A type of comparison a simple arm wrestling contest would never solve. With how much Spinosaurus commanded public attention in the 2000s as a supposed rival to Tyrannosaurus, it's easy to understate how much hype there was with the giant of the South versus the tyrant of the North in the mid-90s. A prominent display was set up in the Academy of Natural Sciences Museum in Philadelphia. One of the first public reveals for Giganotosaurus in a place people could come and see the cast skeleton for themselves. And where was it? Right across the hall from a cast of the AMNH 5027 Tyrannosaurus specimen. The two titans facing each other as if they were in a standoff about to clash with museum visitors getting ringside seats. Two of the very first and sadly very few documentaries covering Giganotosaurus, Beyond T-Rex, and an episode of Paleo World, Clash of the Titans, further leaned in on this comparison and featured such scenes. Two of the very first outings for Giganotosaurus in popular culture, James Gurney's Dinotopia and a sequel film to The Land Before Time, both featured confrontations between the two beasts. They continued to face off in video games and books long before a clash was brought to the big screen almost 30 years later in Jurassic World Dominion. Giganotosaurus was practically defined right out the gate by comparing and contrasting it with Tyrannosaurus. Its identity was essentially South America's answer to North America's tyrant lizard king. But was this all hype? Was there ever a firm answer on which one of the two was the largest land predator that ever lived? Let's take you back to the 90s. The first remains that could be described as the southern giant were discovered in 1993. Like many fossil discoveries, they were first uncovered by chance by paleontologist Ruben Carolini in Patagonia, Argentina, in a layer that is part of the Carnivorous Formation. Perhaps fittingly, Patagonia's name literally means land of giants because of comparisons made between the tall locals and a giant in a popular Spanish novel. The Carnivorous Formation is typically dated to between 99 and 97 million years ago, being part of the beginning of the late Cretaceous period, and would have seen dinosaurs of all types populating large open floodplains and swamps. Giganotosaurus would have coexisted here alongside various terrestrial crocodilian relatives, the armored jacapil, the large abelisaur Acrocanthosaurus, and a wide variety of sauropods from the relatively small Andysaurus and Limesaurus to a still as yet undescribed Titanosaur comparable in size to the colossal Argentinosaurus. The remains of the giant theropod were extracted over the following year and received publication by Rodolfo Coria and Leonardo Salgado in 1994 in the Journal of Vertebrate Paleontology. The findings consisted of a reasonably complete holotype specimen, MU-CPV-CH1, that was largely only missing portions of the skull, the forelimbs below the shoulder, a few pieces of the tail, and the hind limbs below the knees. A second specimen consisting of just a single bone, called a dentary, which is the tip of the lower jaw, was also found. Loose teeth and footprints that might be from the same dinosaur have also been identified. Coria and Salgado named it Giganotosaurus carolinii, or Carolini's giant southern lizard, after its discoverer. It was easily the largest carnivorous dinosaur ever discovered in South America. Coria noted the specimen was probably just north of 12 meters in length and broadly comparable in size to many Tyrannosaur specimens. While the initial discoverers didn't outright declare the new colossal carnosaur the new king of the carnivorous dinosaurs, the media immediately made the comparison. It seems like every time Giganotosaurus was brought up, people just couldn't resist asking the question of whether it might actually dethrone the king of the tyrant lizards. But with a fairly complete holotype, it should be pretty easy to tell if this colossal carnosaur really was bigger than Tyrannosaurus, right? Unfortunately, this is where it gets a little tricky. When determining the typical size statistics for a population, sample size is definitely important. In wildlife studies, it is not unheard of for zoologists to sample hundreds, potentially thousands of individual animals when doing survey work. For example, a 2016 study by Moorfeld and colleagues in +1 on elephants in captivity had a relatively small sample size of over 230. Studying non-avian dinosaurs to this degree, however, is just not currently possible outside of a few exceedingly rare exceptions. Tyrannosaurus is the best sampled and studied macropredatory dinosaur by a wide margin. If we discounted all specimens in private collections, there would only be about 50 T-Rex specimens in museums and universities to work with, and not all of those are very complete. This means getting an idea of what the average Tyrannosaurus was like is only going to be speculative at best. There certainly is something to estimate at least, but the sample size is not nearly as big as you'd need it to be under ideal circumstances. Giganotosaurus has all of those problems multiplied. There is only one fairly complete specimen, the holotype. Even though the description paper was well done and crossed all the T's and dotted all the I's, it didn't provide the same amount of work one might find in something called a monograph. A monograph is a publication that goes into extreme detail about the remains of an organism, often down to every individual bone. Usually this involves the holotype for the species, but can include more than just one specimen. Giganotosaurus did have some of its remains detailed, with photographs and measurements, but there is a lot less information than one might think or need. This means that accurate measurements and their verification can get a little screwy. There has been extensive work on individual bones from the original holotype specimen, such as a 2002 survey of the brain case by some of the original authors. This certainly gives a lot of insight into the internal workings and diagnostic parts of the species, but not too much information about the overall body, as these efforts were not concerned with that. It might be possible to describe Giganotosaurus as one of the best known of the poorly known dinosaurs. Major work like a monograph takes a lot of time, focus, and especially funding, and with many Patagonian researchers having other projects to juggle, including brand new discoveries, there just hasn't been enough time to get that monograph. There are several readily available casts of the holotype specimen featured in museums around the world, such as the US, Japan, and Australia. These casts were first made by Mary O'Donnell in the 1990s. The holotype fossils are currently locked into a floor mount in the Ernesto Bachmann Paleontological Museum, So, for most, cast skeletons are all anyone has access to for research. Comparisons between the various casts and the measurements supplied by the original paper indicates they are similar enough to produce reasonably accurate results. However, there were several chunks of the skeleton missing, such as the lower extremities and portions of the tail that could be important to figuring out certain metrics like height. Additionally, since 1993, there have been several close relatives of Giganotosaurus described, such as Mapusaurus, Meraxes, Tyrannotitan, and Torovenator. Each of these South American Carcharodontosaurs is a reasonably close relative to Giganotosaurus, and cross-referencing between them all can help patch up certain missing parts. This is why the very elongated and flat skull reconstruction from the 1990s casts has, over time, morphed into the bulkier, thicker, more triangular modern reconstruction. Same goes for the eponymous North African Carcharodontosaurus. Rodolfo Coria and colleagues are reportedly currently working on a more in-depth publication about Giganotosaurus, which hopefully might come out in 2025, but who knows. Shedding more light on how some of the measurements of certain bones are made and the dimensions involved might help clarify a lot of details. In the meantime, though, using the material that is available in more formal publications, as well as other resources like 3D scans produced by different author teams, independent researchers, and various artists, seems like it's good enough for now. These reconstructions can be quite good, even if they do vary from one another. They vary due to differences in methods used, confusing details about the fossil, and not every bone discovered has the best photographs. Still, the holotype specimen absolutely was as gigantic as its name implied. Let me bring in Mr. Man from Animal Planet's
The Most Extreme
to show you. He will probably come in and out of this video as I cover different sizing methods. Giganotosaurus is usually averaged at between 12 to 12.5 meters, 39.3 to 41 feet long, and 3.5 to 3.9 meters, 11.5 to 12.8 feet tall at the hip. It's notable that some estimates may increase or decrease these figures by about half a meter or so, as certain parts differ, like the number of vertebrae in the tail, exact lengths of certain limb bones, and how much cartilage is placed in between the vertebrae. Thanks, Mr. Man. At these lengths and heights, Giganotosaurus would fit comfortably within the spectrum of publicly available Tyrannosaur specimens. The holotype Giganotosaurus is longer and taller than certain Tyrannosaur specimens like the Carnegie Museum's holotypical CM9380, but likely smaller than the Field Museum's SU, while being roughly comparable to many others. However, when people discuss what is the largest of some category, how much matter you have is more important than how spread out that matter is. The African bush elephant is the largest living land animal, despite being shorter than the giraffe, after all. So, what about mass? Traditionally, theropod mass was estimated using a funky little formula that took in the femur circumference and spat out some masses. This was popularly codified originally by Nicolas Campione, David Evans, Caleb Brown, and Matt Carano in a 2014 publication in the British Ecological Society's Methods in Ecology and Evolution journal. One frustrating aspect of this, however, is that measuring the femur bone isn't always done with standardized methods, and unless the source of the measurement stated what portions of the bone they were measuring, from what distances, and with what kind of equipment, one might accidentally wind up comparing apples to oranges if two different measurement methods were used on two different animals. The Giganotosaurus holotype's femur is usually listed as 143 centimeters or 56 inches long, and 52.5 centimeters or 20.6 inches in circumference, but the exact numbers might vary depending on the source. Some have raised the concern that the femur length might be overestimated, and it might be shorter than is currently reported. Additionally, the way that certain measurements were made in the past may not have always used the same standardized practices more common today. With conflicting information about how big the femur is exactly from various measurements or scans, figuring out scaling can be extremely difficult from the femur alone. Everyone can agree it's big, but exactly how big and in what ways is the tricky part. That monograph with more diligent estimates would really come in handy here. Still, this is quite large, comparable to Sioux in length, though not as wide around. Measurement methods like this often wound up shrinking Giganotosaurus down to around 6 tons. At that size, the southern giant starts looking noticeably lighter than a majority of known adult Tyrannosaurus specimens. There are 2 caveats with this, however. Femoral circumference-based allometry isn't necessarily the best way to estimate mass for individual animals. Further refinement of prior findings and estimates noted that using such methods might wind up underestimating the true mass of a subject, especially for a biped. Instead, such metrics are perhaps more useful for understanding trends in evolutionary families over time. Let me just real quick, allometry is the term used to describe how scientists figure out how different body parts of an organism change relative to other body parts as the critter increases in size. It's a back and forth between body size and how that body size functions. Okay, back to the rest of the thing. Adding on to this, Romain Pintore, John Hutchinson, Peter Bishop, Henry Sy, and Alexandra Jose published a paper on the evolution of femoral morphology in giant non-avian theropod dinosaurs in 2024. This team found that the anatomy and dimensions of certain femur traits might not directly correspond one-to-one with size. Tyrannosaurs and carnosaurs independently evolved large sizes and arose from different ancestors. So, certain proportions might be down more to evolutionary relationships and other factors on how the animal moved around than just size alone. In other words, both Tyrannosaurus and Giganotosaurus were huge, but how their bodies managed that size down to their proportions of their femuri might not be one-to-one since they are from different families. Donald Henderson published work in 2023 on how growth constraints set an upper limit to theropod dinosaur body size. In the paper, he suggested the pelvis might be a good indicator of the mass and size of a theropod, since all of the load-bearing, as well as the support for the upper and lower body, is at the hips. The reasoning goes that the size of said hips is a good indicator for the rest of the body. This kind of data isn't available in all cases, such as specimens only known from individual bones. But for Giganotosaurus, this absolutely could apply, given the holotype had a virtually complete set of hips and upper leg bones. Using this method, Henderson found the total body length was likely around 12 to 12.5 meters, or 40 to 41 feet long. This is noteworthy as this is essentially spot on to the original estimates Correa gave to the animal back in the 1990s. Volumetric analysis like graphic double integration, or GDI, has been seeing more use in body size estimations. Since living animals tend to have a majority of their body tissues mostly composed of water, the average body density of an animal tends to be fairly close to water too. It really works best if there are complete enough remains to create a reasonably accurate 3D model to account for tissues that heavily contribute to body mass, like organs, fat, and muscle. It should be noted that there aren't any published scientific works for Giganotosaurus using volumetric analysis yet, but the methods do check out and similar works have been done on other species. Building around the frame of the holotype specimen as conservatively as possible, various sources have estimated the body mass of the Giganotosaurus holotype to be somewhere between 7,800 to 8,800 kilograms, or 8.6 to 9.7 tons. A giant indeed. Compared to reasonable estimates for various other large theropods, this puts the Giganotosaurus holotype right in the spectrum for Tyrannosaurus size yet again. There aren't enough specimens to estimate how big the average Tyrannosaurus was, even though it is one of the most specimen-heavy theropod species known, so Giganotosaurus is in an especially sorry spot. No one can tell from just one specimen if the Giganotosaurus holotype was larger or smaller than is typical for its species, but it does vindicate that this carnosaur was in the same size class as Tyrannosaurus. This estimate is also noticeably smaller than some of the higher estimates for how big particularly large Tyrannosaurus specimens like Sioux are, but it is handily larger than many other Tyrannosauruses. there is the presence of another dentary bone, classified as the Paratype for Giganotosaurus carolinii. However, scaling from individual bones is always very tricky. The holotype specimen does have the exact same bone for comparison and does appear to be smaller than the Paratype. Various estimates on exactly how much larger the Paratype is than the holotype have been proposed. These have involved everything from the gross dimensions of the jawbone itself to the spacing between each tooth. Independent researcher and paleoartist Dan Fulks considered it probable that the dentary Paratype specimen was around 6% more massive, but he had his reservations. It's possible the Paratype had a particularly large gigachad chin, but it's also possible it might be the holotype who is disproportionate one way or another. Just for shits and giggles though, let's add in what other size fanatics have found. Estimates of the Paratype from various sources have it at between 3 and 8% larger than the holotype, with most estimates being between 4 and 6% larger. If the square cube law is applied to the estimates for the holotype, this puts the Paratype at between 9.6 and 10.6 tons. At that size, it's rivaling some of the larger Tyrannosaurus specimens. These numbers, of course, are extremely tentative and need to be taken with multiple piles of salt. These could absolutely go up or down, depending on specific measurements used and any future data. For example, Giganotosaurus could wind up noticeably skinnier or bulkier than is currently expected, or it could end up overall longer or shorter. Current volumetric models might be entirely too big, depending on what new data a more thorough survey of the skeleton might yield. What these estimates do provide, however, is at least the best answer currently available for the question, how big was Giganotosaurus? That answer, in a roundabout way, is almost exactly what Dr. Correa said back in the 1990s. The southern giant is roughly the same size as Tyrannosaurus. Plus, there's always individual variation. Individual variation can heavily impact the size of random members of a species. Individual genetics, age, time of year, and health prior to or at time of death can all drastically impact how long or tall an animal grew. For what is known about the specimens involved, Tyrannosaurus does have the largest individual theropod dinosaur specimens. However, the one good specimen of Giganotosaurus that does have good data does put it within the spectrum of sizes the tyrant lizard king is known to be in. What nebulous material exists from other specimens implies the species might have had the potential to grow even larger. Meraxes, a slightly younger relative of Giganotosaurus, was initially only known from a holotype specimen as well. It was actually some information from this holotype which helped revise reconstructions of its older relative. By scaling comparable parts from one another, Meraxes' holotype indicated Giganotosaurus' skull was broader than previously reconstructed and might have had a length of over 1.6 meters or 5.5 feet. The Meraxes holotype was large for a theropod, but seemingly noticeably smaller than some of its fellow South American shark-toothed relatives. But in 2024, a new specimen of the same species was described that was noticeably larger than the holotype, being closer in size to the Giganotosaurus holotype. What I'm saying is that it's very unlikely the first specimen of a new species found is going to be the largest or smallest of its population. Preservation bias, population demographics, and a lot of other factors all contribute. Perhaps with more fossils of both Giganotosaurus and Tyrannosaurus, the question of which of the American continents actually had the largest terrestrial land predators might be more thoroughly answered. On an individual basis, Tyrannosaurus still holds the record, with giants like Sue and Scotty. But on a species-to-species comparison, we might have to call it a draw for now. For more interesting stories about nature, the history of life, or what goes bump in the night, subscribe, like this video, drop a comment in the comment section below, and hit the bell icon to stay in the know with everything Edge. Thanks for watching.